So today I'm going to be talking about designing specifically quantum codes in a similar fashion to what Nicholas was talking in this like with hypergraphs and some other things for very specific constrained kind of modular architectures. So these could be architectures that I'll mention that in a second. But this is work with Lucas Berendt from Technical University of Munich. He should be also here somewhere in the audience. And yeah, if you want to check out the very specific details of the paper, there's the archive link. It should also be appearing in PRX Quantum very soon. But this presentation is going to be very graphical. I'll try to exclude a lot of technical details and just try to convey the most important ideas. So I think yesterday, so those people who actually stayed for the industry talks, you guys had a really good introduction from New Quantum about why we should care about modular architectures. As we were to scale the quantum computers to bigger and bigger sizes, then at some point it becomes very costly to have everything on a single kind of chip. So obviously ion traps here at New Quantum are thinking about modularizing their architectures, but even like semiconductor platforms are doing something similar whenever their chips become like too big and there's some kind of like modularization happening. So the goal of this talk and my research is to design error correcting codes that are supported on these architectures. And not necessarily that every single kind of smaller module would have its own error correcting code, but that we can exploit the full modular layout for, let's say, one or very few error correcting codes that are fully compatible with it. So the talk outline is as such. I'm gonna very briefly introduce a little bit of a representation of classical error correcting codes and then also quantum error correcting codes, but Nicholas gave a really good summary already. I will build upon that. Then I will talk about recent results in surface code architectures and how they can be used to obtain multiple surface codes and even like three-dimensional surface code. And then finally, I will generalize some of the results even further to general modular architectures and even further generalize it to some interesting kind of layouts and so on. So let's get started. Let me actually use a pointer too. So we represent classical codes, linear classical codes we can represent with a parity check matrix. So here every single column represents a bit and every single row is representing a check. And basically we say that we are checking the parity of those bits that are like ones in some row of a specific check. There's slightly different representation, which we can also use for classical codes, which is the hypergraph representation, basically. And here it's just a graph, no hypergraph, but this is just kind of like I chose the code to be simple enough so we can represent it as a graph. But there's a one-to-one mapping with this parity check matrix where essentially we have bits on the edges and checks on these vertices. And you can see that if we identify the first row with the check number 1 and the first two columns with bits number 1 and 2, and here they are represented by edges and a check is this vertex. And to show that essentially in this first row we have ones in the first column and the second column, then that means that these two edges are adjacent to this vertex that represents the first row. Right, so this is just another way of looking at classical error correcting codes. And there is one more representation that people also sometimes use, not so much for classical codes, but definitely it will become important in quantum codes. And this is using so-called chain complex formalism, where this is a sequence of vector spaces. And you can think about it as the first vector space is just a binary vector space with bases given as these edges, and another vector space is a binary vector space with bases giving as these vertices. And then there's some map, which is called also boundary map, which you also heard a few talks ago about, so in terms of simplicial complexes. But essentially, it maps edges to vertices, and it works exactly like a boundary map you would expect. So if you take a look at this edge number 1, and you map it to vertices, it would be mapped to this vertex and this vertex, because those are essentially the boundaries of this one edge. Finally, it's very trivial to map these kind of hypergraph representations of classical codes to their connectivity codes, or so-called also Tanner codes that were introduced also in the previous talk, where we essentially just take every single edge and we augment this kind of graph with vertices on basically every single edge. And now this is a bipartite graph, which was the Tanner graph also from the previous talk. So we're going to do something very similar now for the quantum case. And the idea is that we can deal with bit flip and phase flip noise separately. So these are so-called the CSS codes. So we're going to take 2 of these parity check matrices, one which detects the bit flips and one which detects phase flips. And we have this criterion that we need to satisfy for CSS codes, such that basically the stabilizers of parity checks from one matrix and parity checks from the other matrix need to commute, which is equivalent to writing it down in this form. Again, we can represent it in terms of higher dimensional hypergraphs, where we have vertices, edges, and faces now as well. Faces right here is in a slightly an asterisk form, because they don't really always map to faces in the graph theoretic sense. And the faces would be then kind of like representing the Z checks of the code, and vertices, X checks, and qubits are again still on the edges. And in terms of the chain complex formalism, we have this kind of 3-term chain complex now instead of 2-term, because we have one additional vector space, which are the collection of these faces. And the chain complex has this very, very specific property that the boundary of the boundary disappears, as we heard 2 talks before, and that is exactly the kind of like stabilizer commutation relation that we require for the code to be valid. Again, in the quantum setting, we can map this kind of graph to a connectivity graph. So this would be a Tanner graph, tripartite graph. And this is specifically important whenever you start designing architectures for some error-correcting codes, because this is essentially how you would be connecting your ancilla qubits and data qubits in your quantum computer. And there's like all these different kind of representations on this slide and the previous slide, and I will probably jump from one to the other quite often, but it's quite straightforward to see the links, and especially seeing this kind of the mapping from the chain complex representation of a like high-dimensional hypergraph to the connectivity graph of the Tanner graph. That will be I will use that throughout. Black dots. So these are just basically vertices, which belong before to the edges. So again, we map edges to a new set of vertices, and we map faces to a different new set of vertices. And you can see how they are connected, but basically the faces are connected to the vertices representing the faces are connected to the vertices representing the edges, but they're not connected to the vertices representing the, let's say, vertices. So, all right. So, also listening to the Nicholas talk, I think I might have gotten this year wrong. I think in his talk it was 2009. I'm not sure who is exactly correct, but I guess you can excuse me because I still was in high school at that time. I wasn't reading quantum error correction papers. But basically, Tillich and Ziemer proposed a way to make sure that the CSS criterion is fully satisfied. And what I did is that we can take any classical codes, or like essentially constructing a quantum code from 2 classical codes. And we do that where essentially we add extra So we take tensor products with identities in this form, and we construct two parity check matrices. And as long as these identities have the specific dimensions, but that's not so much of it's important, but not right in here for the presentation, then you can very quickly check that this CSS criterion is satisfied right here. So basically, we are forcing the commutation of these two parity check matrices to work by introducing a tensor product with identities. The problem with this is that the identities are essentially giving us no extra protection for the code itself, and it increases the number of data qubits that we require. So now the distance of the code, even though these A and B could be really good classical codes themselves with really good protection, the quantum code constructed in this way with using a tensor product with identities is lacking this, for example, linear distance scaling that you would see in classical codes, just because, yeah, the identity doesn't really give you the protection. It's only there to ensure that the commutation works. So to see this, it's always nice to have like a very specific example. And let us just construct very quickly so-called the hypergraph product code that you also heard in the previous talk. Let's take A and B to be two repetition codes. So these are their parity check matrices. You can also represent it as a cycle graph. And if we were to just cut one edge open, stretch it out in a single line, and then identify this edge with this edge, it's essentially just a different way to represent the graph. And now let's take a look at the first parity check matrix that is detecting the phase flips. Here we have two different terms, so we're going to go through those two terms separately. The first one, we take this A code, so basically this straight line, and tensor it with identity, so we obtain something like this. For the second part of this parity check matrix, we do the same, but we are swapping the order, so we look it ends up something like this. And once we put them both together, so we obtain your parity check matrix, we obtain this kind of grid-like structure that many people know about or associated with the surface code, or in this case, this is the Tori code because we have the opposing edges identified. So this is also one of those codes that achieves the square root of n distance scaling, but if we want to construct better codes, we better start moving qubits around or doing some kind of long-range connectivity that we saw also in the previous talk. And shuttling is one of those options. So for example, to entangle some qubits which are far away in our architecture, we might move one qubit a bit closer to that qubit, have some maybe local entangling operations, and then move it back to the initial starting point, for example. Here, some shuttling ideas have been explored in ion traps, but also similar shuttling ideas have been explored for silicon quantum computer architectures. And I'm going to be talking about one of those kind of ideas that arrived from silicon quantum computing group, which is here presented. Oh, this was an idea by Zhenyu Tsai, Adam Siegel, and Simon Benjamin. And in this kind of construction, what they did was they considered the surface code layout of their quantum computer. We have these green Z parity checks, again, being the faces of the code. And then on edges, we have the data qubits. And then on vertices, we have these X parity checks. And in this architecture, they took all of these elements and replaced by a loop of qubits. So a loop of actually a shuttling loop. So every single qubit in this loop can be moved around. And again, so the layout is still exactly the same, the surface code layout, but instead of just single elements, we have a loop of shuttled qubits. And as they move around, they enter these kind of entangling regions. So these are the dashed boxes right here. And they would entangle with the data qubits, which are represented by these black dots, would entangle with either the X or Z parity checks. And then we do some kind of, these loops would be also appended with some measurement kind of devices, and then we can read out what the ancilla qubit measurements are, and we can do error correction. And they show that basically replacing each individual element of the surface code, which initially would be just a single kind of qubit. With these loops of qubits, we obtain a stack of surface codes. So instead of just a single surface code, we have a stack of these surface codes. Right. So our idea then was to take this kind of construction or example construction and try to formalize it a little bit in terms of these tensor products of maybe some other codes, just like we would take a hypergraph product code as a tensor product code of two classical codes. So then we were trying to think about what are these two objects A and B. So A could be the surface code itself, but then so what's then B? And the B is essentially a code with 6 checks but 0 data qubits. So you wouldn't really call it a code, I guess. If you were to look at its parity check matrix, it would have 0 columns. Not really like a sensible object, I guess. But it does make sense whenever we look at it from the perspective of the homological algebra and these sequences of vector spaces. We can just have the quantum code, again, represented by a 3-term chain complex, and this, whatever that is, just a single vector space. And if we take a product of these two, so a tensor product, well, essentially what we do is take every single vector space from this quantum code and tensor it with this vector space from these essentially 6 or whatever number of checks. Then we obtain a new code that is fully representing this stack of the two-dimensional surface codes. So the next idea was to maybe put something more sensible inside of these kind of loops. So not just fully independent 6 checks, no data qubits. But what about if we take one of those loops and actually dedicate some of the qubits to be the data qubits and some of the qubits to be the ancilla qubits? So this is the connectivity graph I was previously talking about. And now you can think about it that this is essentially a code that is living already in this, like the shuttling track. And this is here given just a simple repetition code, again, represented by some 2-term chain complex. And we want to argue that this will give you a possibility to construct a 3-dimensional surface code. So how we argue about this is that we can think about, again, so the code within this shuttle loop is just a repetition code. Then the layout of the loops themselves was the 2-dimensional surface code. So that was the initial kind of starting point that we started with. And you think about the repetition, so you can formulate it fully in terms of modules themselves, where the code inside the module is representing the intramodular connectivity, and the layout of the modules is the intermodular connectivity, and that is represented by some other code. So if you take a tensor product of these two codes, we obtain this 3-dimensional surface code. And what we also show in our paper that this is actually the case. So if we were to have repetition loops, and we allowed this kind of like entangling as they go around, and we allow this entangling with the nearby loops, but we also have some kind of entangling happening within the loop itself, so as to like read out this kind of repetition code, then we were able to show that this produces a 3-dimensional surface code. Here I haven't really dedicated any of the edges or vertices to some specific elements of the code, because there's some kind of a freedom given to you, so you can have like data qubits either or faces in this vector space or on edges in this vector space. But that's up to the experimentalists themselves to decide. So this was like an idea about shuttling, or like how we slowly come from this looped pipeline architecture to more general constructions. And what you could have also is, or like at least many architectures are considering, are long-range entanglement using photonic links. So shuttling was more of like very local. As you go around the loops, for example, then you locally entangle with something. Here, for example, Christopher Monroe's group are considering whether you have some logical units representing some, let's say, multiple, or like an ion trap or something like that. And you have some photonic links that through which you can generate entanglement between qubits and distant ion traps. And that also gives us a chance now to actually produce the long-range entanglement that is necessary to create better codes. So we wanted to now generalize our construction to this setting, and to do so, we wanted to introduce modular architectures in a way where we have some kind of collection of physical qubits that constitute your quantum computer, and we partition them into modules. And these modules themselves are, so there's some kind of connectivity graphs within the module. So essentially how the qubits can be entangled with each other. So this is one graph. We call that intramodular connectivity. And we require that for every single module, this intramodular connectivity is the same. That's one of our assumptions. And the next thing is that there is some kind of graph that also describes how the modules themselves are connected in some network. And then that is called intermodular connectivity, and we require that if the two modules are connected, let's say M1 and M2, then there's a possible entangling link, or like entanglement can be made between respective qubits of each module. So, and here, it makes sense to talk about respective qubits because every single module is exactly the same construction. Now, if we take two, let's say, classical codes, we map them to their connectivity graphs right here. So remember, they can be represented by, for example, these hypergraphs, and then they can be mapped to the connectivity graph. So these are their Tanner codes. And let's say the first code has the connectivity or Tanner graph G. The other one has G prime. And our main result in the paper is that if G and G prime are subgraphs of the intra and intermodular qubit connectivity respectively, that is, one of these kind of graphs, let's say, define what is the connectivity graph within the module, and the other graph defines what is the connectivity between the modules themselves, as defined before, then we can construct a new code, which is this hypergraph product code, for example, quantum code E, that fully respects the connectivity constraints of your full architecture. So this is like a framework or a formalism that allows us to create new codes for modular architectures in this manner. We wanted to generalize a little bit further and consider more exotic codes that appeared also very recently, 2020, by Hastings, Hand, O'Donnell, where they thought about these hypergraph product codes, but they also thought that we can introduce some kind of twists to increase the distance of the overall code. And we now generalize this formalism where if we're allowed that it's not just, the respective qubits need to be entangled with the respective qubits to have the module 1 connect to module 2, for example, we have some kind of twists which are allowed between these connections. And these twists will be the ones that will actually, that will give us better performing codes. And in the homological algebra perspective, we have a code which is the base code and a code which is the fiber code. And these are called also fiber bundle codes because they come from algebraic topology of fiber bundles, where we have some base, let's say this is the Tanner graph, and on this as you move from one element on a base to a different element on the base, the fiber gets twisted in some way. And this will give us a possibility to construct better codes. Now what's very interesting is that here you can see that D is now the first argument in this equation and not the second one. It seem very maybe trivial, and maybe some people might think that this is fully symmetric, but it's not really, because we really want to think about twists as the twist just between the modules themselves. Because if we were to switch the base and fiber around, where essentially the base is the intra-modular connectivity and the fiber is the intermodular connectivity, what you would end up is that most of the connections within the module are actually disappearing. And now we have only intermodular, most of the connections are intermodular. And we assume from a physical perspective that these connections are very more noisy, less easier to make, and maybe take also a longer time to establish. So then we don't really want to do that. We want to do the really nice twist just between the modules themselves. So it's very important to correctly identify which is the base and which is the fiber. So doing so, we have had an example code construction where we considered a loop again as each single individual module of loop of qubits, which represents this repetition code. So you have ancilla qubits and data qubits alternating, and they can entangle only like with the nearest neighbors. Yeah, so just like in the previous setting for shuttling kind of option. And now the way the modules are themselves connected together, we took that to be a random LDPC code. So basically an arbitrary graph, which has low degree. And we obtained a new code, which is about, in terms of the code properties, at least has 5 times reduction compared to the surface code. So this is very interesting because, yeah, so basically we were showing that this construction allows you to construct better codes where in each module itself, it's a very simple repetition code, but the modules themselves are connected in some more fancy way. And we have this kind of twists being allowed between the modules themselves. And with that, I think this is just like one of the first steps and works for designing error-correcting codes for very specific architectures. And I think there should be way more work done because it's hard to have it's hard to just come up with one universal best code that will fit for every single architecture. And I think that will just not be the case. Thank you for listening.
Thank you so much. We have time for roughly one deep question or 2 shallow ones.
Thank you for the really nice talk. It will be a shallow question, but have you considered also other type of connectivity where, because for some architecture you have only one connection outside of the node and not all connection?
So you're referring to this kind of
yeah,
right here, this the kind of setting?
yeah.
Yeah, so this is a good question. I often get it from experimentalists asking, well, can we just reduce the number of connections between the modules themselves? And at least from like the theoretic sense, it's not so trivial because there are some bounds on how good of an error-correcting code can you make if you can easily separate the connectivity graph into smaller pieces, basically, which are disconnected. Like how many links can you cut to disconnect the connectivity graph into smaller pieces? And you can think about it if there's like very few connections right here, let's say just one or like some constant number that doesn't grow with the full architecture size, then you will be able to separate these two modules very easily. And that kind of gives you a limit of how good error-correcting codes you can obtain. So in some sense, we cannot avoid this if we want to have a code which is across the full architecture.
Thanks.
And by code, I mean a good code.
Dan?
That was a great talk, Armands.
Thank you.
I mean, thinking about this sort of cartoon of a quantum computing architecture, you might imagine that if one were to construct this, there would be different noise levels in the different kinds of links and operations. Is that something you've considered, and do you have any results on that?
Yeah, no, we definitely have considered, but I have no results. I think it's a really interesting question. We really wanted to just put the formalism on, but exactly here, so that's why, for example, I wanted to have completely separate 2 graphs, one representing the connectivity between the modules, one within the module, because we already assumed that the connectivity within the module is going to be cleaner, faster, like less noisy, and the connections between the modules are going to be the rough ones, or like the long ones, and you might not be allowed to get like that good of a connectivity graph between the modules themselves. We haven't done any kind of results, but this is one of the motivations for this work in general.
Thank you.
Thank you so much for that. Let's thank the speaker again.